Okay, you can start if you're ready, and I will record the time for you.
Good afternoon, everyone. My name is Marvin Hong. Today,
Take the mic. Take the mic.
good afternoon, everyone. My name is Marvin Hong. Today, I'm going to talk about the implementations of autonomous driving in Hong Kong international airports. So, to start with, let me give you a brief background of Hong Kong International Airport first. So, as you may know, HKIA is one of the world's busiest cargo airport. To give you an instance, in 2023, it reaching about approximately 4.3 million tons annually. Besides, it's also ranked as the busiest cargo airports in the world for about the 30th time since 2010. This underscoring its vital role in global aviation and logistics. But currently, it's having some kind of challenges. For example, how to handle the massive logistic needs in Hong Kong IA has always been an issue, as most vehicles used in the industry to deliver heavy cargoes are operated by human drivers. However, Hong Kong's always suffered from the labor shortage and rapid rising salary. For give your instance, so there's about 25 shortage of drivers in cargo transportation companies at Hong Kong International Airports in 2020. 30% compensations increased it for over the past 5 years, and overall limiting its throughput capacity, affecting its roles in the global. So, the key objectives of implements of autonomous driving is to improve the overall operational efficiency. As the operation is not affected by various external factors like the drivers or either the bad weathers, and even avoid the occurrence of accidents by not using the human drivers. Overall, giving a more reliable, safer solution than the traditional human driving vehicles. So, for the application scenarios and the related work for the autonomous driving vehicles, for example, the autonomous driving could use it as to deliver cargoes, materials in the airport powers and automated warehouse environments. Also, it can portray the restricted areas like the one-way border, personal transportation, between in the restricted areas. As these environments are often semi-structured and unorganized, covering their expanses areas that include both indoors and outdoor pathways. So here's the current implementations of autonomous driving vehicles in Hong Kong International Airports. There's have autonomous driving tractors, the AETs, since the December of 2019. The autonomous patrol cars, APC, since September 2021. And finally, autonomous shuttle buses, the ASB, since May of 2023. So, for the areas of applications for the AETs, so I've been used it as the logistic and ground operations, including handling the baggage, transfer departing luggage directly to aircrafts, as well as transport of large luggage. Besides, it can also operate in the cargo aprons, transfer air cargos through cargo aprons, and special mention it can hold up to 30 tons of cargoes. So as the December of 2023, there's about a total of 41 AETs are actively in use. So for the APC, it primarily use it as the airport security and the surveillance. So it patrolled along the south and the north runway roads 24 hours a day. Issue a signal warning if some personnel get too close to the border fence, and also alert on the duty security staff. So also as December 2023, there's about total of 2 APCs are actively in use. So lastly, for the ASP, its primary use at transportations. So it can bring the restricted areas transport. It can carry about 40 airport staff to work in various locations across the airport's restricted areas. So for the technologies that have implemented into the autonomous driving, there's about 2 critical. So firstly, let's talk about its advanced sensing system. For the autonomous driving, it's usually installed with the LiDAR sensors for collecting the surrounding 3D points cloud data. Besides, it's also equipped with the wide-angle high resolution cameras and real-time kinetic GPS, inertial measurement unit, and external encoders to generate real-time audiometry information stably. So here is the actual photos of an autonomous industrial practice deployed in the Hong Kong International Airport and its sensor system. As you can see, the 3D sensors are installed on top. Besides, we have the front wheel cameras and the rear wheel cameras, GPS antennas, IMU's controller encoders. Besides, there's additional 2D sensors, safety lasers to emulate sensing blindness and avoid obstacle on the ground. So for the control system, first let me introduce to you the hardware architectures of the autonomous driving first. So there's about 4 systems. The task planning system, which consists of task planner and a long range radio unit. Second, there's a perception, localizations and planning system, which consists of the front and rear view cameras, 3D laser, GPS, internet switch, and host industrial PCs. Thirdly, we have the motion control system, the inertial measurement unit, the 2D lasers, and the external common filters, encoders for fusion the initial measurement unit, 2D lasers, and so finally we have actuators who include the gears, steering throttle, water motors for controlling the movement. So give you an instance, there's a schematic overview for the core system. So if commands are given to the autonomous driving system, the host IPC industrial PC will receive tasks from the human machine interface, the planning system for the long range radio units, and then the host industrial PC will generate a feasible local path by searching the road maps, combined with the updated environment maps, consists of the vehicle poles, surrounding objects, visual information, and odometry data from the 3D lasers, GPS camera, and so. So then the feasible local path will transfer to the PLC, the programmable logic controller for the intellects. Then the PLC will feed the path into the motion control modules, generate velocity values by comprehensively considering the local path curvatures and detect obstacles. And finally, input those velocity pedals into the steering throttle and brake motors to achieve moving capabilities. So for the multi-sensor fusion basic perception section, so as the visual sensors like the front and rear cameras can provide rich information, but always suffer from the limited perception range, and it's sensitive to limitation changes. And besides, the laser-based sensors can provide accurate spatial information and more great at night or the bad weathers, but it have the local sparsity problems. And considering their strong complementary natures, make them ideal for use in autonomous driving, since the industrial environment is usually highly dynamic and narrow. The autonomous driving vehicles need to share the operation environments with a large numbers of moving vehicles and man-made objects. So here's an overview structure of the proposed multi-sensor information future based perception system used in the autonomous driving in the Hong Kong International Airport, which consists of 3 parts: the data fusion and object detection, object tracking, and object motion, estimations part. So firstly, for the data fusion and object detection parts, so it consists of laser detection modules, which can obtaining the laser detection result by the laser point cloud, which reveals that the point cloud belongs to the ground surface, which reduces the measure requirements, the amount of the measurements. Secondly, there's fusion detection modules, which obtaining both the visuals and lasers combined detection results. There will be a visual detections modules, which obtaining the detected visual results, such as vehicles, pedestrians, and traffic signs under various weathers and demolition conditions. So for the second big part, for the visual laser tracking modules, it matching the current result, the object motion animations result, the laser detect result, the visual detect result with the previous result to determine the corresponding object result and update its tracking templates with the latest result. And second, there's a tracking template updation modules, which obtaining the tracking templates which contain the previous corresponding objects and object motions estimations results. Thirdly, there's object motion estimation modules, which using extended Kalman filters to integrate results from the laser and visual tracking modules, and then to estimate the object motion states. Besides, the vehicle motion state and the environments are also considered to obtain the object motion estimations in the global correlations. Overall, it ensures the corresponding of the objects by comparing the previous units to ensure there's no missing detections and false detections. So to conclude, the implementations of the autonomous driving in Hong Kong offers improvement in computational efficiency and safety. So besides by providing the complementary sensors and control system. So this is the end of my presentation.
Okay, it's around like 40 minutes. Okay. So I think this is a good presentation with very clear logics from the the necessity of the auto driving in Hong Kong airport. So I get several questions. So first one is that, so what do you think is, so if you look into the airport, so we still can only see very limited, the deployment of the auto driving cars in Hong Kong HKIA. So what do you think is the major challenge in the front?
Thank you. You can
Yes, yeah, no problem. Yeah, I mean currently, for example, I take flights almost every 2 weeks, maybe in the HKIA. So, but personally, my experience is I almost very few cases I can see the autonomous driving vehicles in the Hong Kong international airports. So even for the petrol purpose or for the cargo delivery, I didn't really see the deployment of the self-driving cars in the HKIA. So of course there should be some challenge in the front. So what do you think is the biggest challenge in the front before the massive deployments of the self-driving cars in the HKIA?
for driving new technologies for the aviation and logistic worlds. So since it's available service in the December 2019, it just stopped its service for about 5 years, which about 41 autonomous driving, which are a very small numbers compared to the whole system. But unfortunately I don't have the data on how many transitions are.
Yes, I see. So currently, recently I think I also see some very inspiring news that the HKIA is going to be adopt the technologies from Baidu to deploy the self-driving cars for a certain area in the HKIA. So anyway, I think still some time to really get this ready. So can you go from the first page? I will just quickly go through and provide some comments to you. Oh, the cover page is very good. So those cars are for the safety patches, right? Okay, I mean three black and yellow cars in the front. So this is for the patcher purpose or okay, next page. That's good. Yeah, it's good. Yeah, I think I love this page. So this page clearly, I mean, illustrates the challenge of the at HKIA. So I think it's good to let us know why. So for example, I mean, this is quite specific in Hong Kong. So for example, if you look into the like Asia area, for example, in maybe mainland China, I don't think the labor shortage and the rising salary is going to be a big problem in mainland China. But in Hong Kong, it is because for each year, okay, for example, for a PhD student scholarship, each year it increase. It's like each year increase to around like 500 to 600 something. So rising salary is a big problem because so this the problem is that the increase the cost in this application. So it's quite good. So next page. Yeah, it's good. So especially for the black range, this is quite typical in Hong Kong. Yeah, that's right. Oh, okay, it's good. No questions. Next page. Yeah, it's good. Yeah, it's good. So this is 2020. This is 2023. Okay, 2023. Okay, next page. For APC. Oh, this is already in use. Oh,
Airport staff.
oh, for airport staff only. It's very. I mean, it's only very limited frequency, right? Okay.
Usually we use it to transport I remember for the local
Passengers. Okay, next page. That's good. Yeah, no problem. Next page. Next page. Yeah, it's very good. For this page, we can definitely. I mean, this page is good. Definitely, from this page, I can learn from this page that what is the typical sensor steps for the self-driving cars in here. So, for example, there are some encoders, 2D lasers, 3D lasers, and multiple cameras, IMU, and controls and GPS antennas. Yeah, next page. Yes, next page. Next page. Yeah, it's good. Go ahead. Next page. So just one more quick question. So, usually if this figure is not originally coming from you. We need to add the citations. Yeah, next page. Okay, I agree with this one. Next page.
It's a file page.
So for the conclusion, I think this is also good. So my last comment is, so for the conclusion, it can be great if you can add some numbers from your thinking or from your insights. For example, I would say like roughly maybe like in the coming 5 years, we can make this ready in HKI with higher operation frequency, something. Yeah. Oh, thank you again for your presentation.
Okay, so this one. Okay, please go ahead. Martin. Yes, Martin.
So, is there a thing?
Oh yes, every record time.
Is there a thing to press to change the slides?
No, let's.
Oh, yeah. Let me- "3D building model-based pedestrian positioning method." So this is a study done by Dr. Lee Ta-Shu, Ms. Yan Lei Gu, and Shunsuke Kamjo. So this is about 3D building using model-based for pedestrian positioning. So all of us know GNSS, Global Navigation Satellite System. It's different from GPS because GPS is just a part of it. A satellite navigation system is a system that uses satellites to provide autonomous geopositioning, and GNSS is a global coverage of this satellite navigation system. So GNSS allows us to locate and make use of GPS, and it has been significantly increased in our globalized community. When we are pedestrians, when we're walking around, we always carry around our phone and our GPS, and it is very necessary for us. And 3 important factors that are necessary for GNSS to work properly is accuracy, the time taken to position, and the update rate. How fast does it change? Does it know where we're moving to and how we're moving? So this is very important. However, there's an accuracy issue that comes with GNSS when we are in an urban canyon like in Hong Kong, due to the many tall buildings that are there. In open fields, even the low-cost GNSS is very accurate, but in an urban canyon, there is multi-path effects and non-line of sight effect. And because of that, there is an error due to the signal blockage of the buildings. So how can we overcome that problem? Well, let me explain first the 2 errors, the multipath error, and the difference between the multipath error and the non-line of sight error. They are not the same. The multipath error is the inaccuracies in positioning that occur when a GNSS signal reflects off surfaces to the receiver. And you can see the problems that it causes is the signal reflection, time delay, and the position inaccuracy. While non-line of sight is the inaccuracies when a GNSS signal is obstructed by a building and cannot reach the receiver directly. And this is obstruction, there's a reduction in signal quality, and there is position inaccuracies. Now, what are the objectives of the solution that was proposed by Dr. Lee Ta-Tzu and his friends and his fellow doctors? Well, the first objective is that to develop a rectified positioning system. There are many proposed solutions for this. However, how can we develop a rectified positioning system to give us the best accuracy and also ensure consistency and reliability in all urban canyons? And many other studies look at the GPS, but they make use of some of the trackers are very high quality trackers. But in this study, we're making use of simple GNSS that are available low cost on your phones. So let us look at the solution. First is the 3D based pedestrian position. That is the name of our solution and makes use of three main things: the 3D building model, the ray tracing simulation, and the implementation of particle filtering. And if you can notice here, there are some particle filtering here. These black dots are the dots that were invalid particles, and these dots are the ones that are the valid particles. Now, let us look into the methodology. Okay, so the 3D building model is based on two main features. When you build something 3D, it has height and it has the X and the Y direction. So first we take from a 2D map the building location in the X and Y direction. Then they were using the fundamental geospatial data of Japan because they did the study in Japan. Then the height of the thing is taken from a 3D DSM, a digital surface model. So once we have the length and width and the height, we can create the 3D building model. And this gives us the combination of the 2D GIS data and the DSM data. Then we move on again to the next part is the ray tracing algorithm. This is used to simulate the signals to find the best interaction of the urban landscape and the signals and the direct path and the single reflection. So this allows us to estimate the reflection delays and also identify which are the multipath signals and the NLS signals. Now, in the methodology, let's go into the first part. So in the calculation steps, we have a distribution of position candidates. First, we are given there is a list of position candidates and there's a distribution of position candidates around a reference. And you can see that around a reference position, this two-dimensional Gaussian distribution, which we have learned about in class. And during the resampling phase, when the person is moving, half of the particles are generated according to the normal distribution, while the other half. Okay, I'm sorry. I think I missed out something there. So there is, as you can see, these are the two differences. This is the random positions that are given, and this is half of the particles are generated according to this formula, and the other half are given due to a time difference. Again, the regeneration. Now, then we move on to the simulated pseudo range from a candidate. So we have to find the similarities between the measured pseudo range and the pseudo range simulated from the position candidate. So the simulated pseudo range can be calculated by the geometric distance, the satellite clock offset equivalent to the distance, and the receiver clock offset equivalent to the distance. And I think you guys have all seen this formula. We have learned it in class. So we have, this is the geometric distance. This is the clock time offset, and this is the ionospheric delay, the tropospheric delay, and the noise delay. So the signals are classified into three signals. One is the LOS, the line of sight signal. So the reflection delay or the reflection error is 0. In that one, we take ERFX into 0. What about the NLS, line of sight, NLOS signal? The signal reflection is the reflection path minus the line of sight path. But it is different from the multipath because the effect on the pseudo range is much more ambiguous because we have the reflected signal and the line of sight signal. So if you notice, this is for the non-line of sight signal, which is the reflection path minus the LOS path. Then we have the multipath error. We have, according to the study that they did, they assumed that the multipath effect is about 6 decibels weaker than the line of sight signal. And the assumed noise envelope is used to calculate the multipath delay. So they equated the noise envelope function to the multipath delay. And you can see here, this is the function that they use, the noise envelope, which is the reflection minus the, I think, the original. And you can see this is what they showed when they were assuming of the line of sight is the multipath delay is 6 decibels weaker. And I think, yes, so the other, okay, no. So the assumed noise envelope is used to calculate the multipath, and you can see the similarities between the measured pseudo range and the simulated pseudo range can be evaluated using this formula here. So we are going to find, then finally we have to calculate the similarities which we were originally trying to find, simulate the pseudo range between the pseudo range set and the simulated pseudo range set. And you can see finally we have the evaluation of the position candidates. Which are the position candidates that are valid and the position candidates that are invalid? And by doing so, we use this formula here. You can see here, if the DPR, which is, I think, the position candidate is less than the CPR, then it is valid. Otherwise, it is invalid. That we saw before is the black dots. And you can see that the estimated position is calculated as the weighted average of the position candidate. So once we have calculated which are the position candidates that are valid, it's quite simple. You just find the average of the data, the position candidate, and you can see we use the confidence level, which we have learned also using the Gaussian formula. So as you can see, the experimentation, this was done in Tokyo. It was done in, I think, I can't read this, Hitotsubashi area, which is a very high urban canyon area, and there was a lot of error here. So they were making use of this environment, and also the data that they collected was from the Japan geospatial data. So you can see they used a simple GNSS receiver, a commercial grade u-blox EVK. And if you notice, this is how they did the experiment. There is an u-blox multi-GNSS antenna on the person that is walking. And then there's a reference receiver that is also employed to collect the QZSS. So they were not only using the GPS signal, they were using multiple other signals from multiple other satellite navigation systems. And then there is an antenna which is attached to the shoulder, as you can see. So they are walking around like this, and that is the data collection equipment. Then they have more equipment for the data recording. There's a ground truth generation. So where is the person exactly? We're recording the data, but we need to know where the person is exactly, right? So they made use of a video camera that is set on the floor of, I think, one of these buildings, and they were able to locate the person precisely to compare the data between the calculated and the actual. And you can see this is the ground truth data. And you can see the green dots are this is the free software that they're comparing with. They're using with the free software. So the testing scenario was that there was a static test when the person is in a controlled environment, and the dynamic test, which is when the pedestrian is moving. Then there was simulation and analysis and the comparison of the proposed methods with the RTK-lib SPP software, which we also did in class, I think. And then you can see that the results and the discussion, the thing outperforms the RTK-LIBB by a long gap, because the RTK-LIBB has a signal difference, error of 7 to 10 meters. But the 3D map model has only 5.1 to 4.4 when we combine all the satellite navigation systems together. And it has only, this system, although only considers the single reflection delay. Only single reflection delay. So there needs to be more work done to have a more sophisticated system to compare with other multiple reflection delays also. And you can see that the RIME FDE technique for position candidate is in the particle filter to exclude abnormal signal measurements. And if you notice this graph, it clearly shows. So you can see there is a GPS. If you can see GPS plus GLN, NISS, and multiple other satellite navigation systems. And the RTK-lib software, you can see that the probability is quite low here, but the 3D map method is almost 1. It's very accurate compared to it. So it is a very good system. And so in conclusion, as you have noticed, the objective and the methodology, we want to improve the GNSS position accuracy for pedestrian in urban environments, not only using high commercial systems, GNSS receivers, and it uses a 3D building model with ray tracing simulations. The experiments validate the experimental setup, and you can see it was done in static and dynamic tests, and there was video recordings and aerial imagery to access the accuracy of the positioning. And as you can see, the results and implication, it is having great potential in the integrated navigation systems for pedestrian applications, especially when combined with multiple GNSS constellations. So when we combine with multiple satellite navigation systems, the accuracy increases a lot. And that's all I have. Thank you very much.
Okay, so Steelers will count on tourists.
Okay, it's around 12 minutes. So can we go back from the first page? Okay, because this is the academic papers, so I mean the logic is great. So from the problem statements to the background to the methodology stuff. So I think I get several questions in my mind. So this question may be a little bit academia. So you can, if you look into results, can you go to the page showing it's like an error plot. It's an accumulated error. This one, yeah, this one. So if you look into this plot, okay, so the x-axis is the errors and the y is the probabilities. So if you look into the 10 meters, it means, okay, 10 meters, 0.9 means 90% of the results is with the error more than 10 meters. It's, around 10, within 10 meters. So what the thing is, so this paper proposed to use the 3D maps to rectify or correct the GPS errors. So why still the error can reach around 10 meters? So what's the reason behind? Based on your understanding.
Why do I think that the error still reaches about 10 meters?
Yes.
Well, I think maybe because the system has not been refined very well. As you can see that there is when we use the system, the other systems use high positioning systems, while for this one it has still, I think, a lot more to go through because it's only using single reflection delays and it's not a much more, it's not using many different formulas to analyze the average. But I'm not really sure why the probability is much higher
Yes.
for the error.
Yes, that's a good point. So for example, in the exact scenarios in practice, so the signal can be refracted by many times.
Yes.
For example, like 2 reflections or multiple reflections. So if you only consider the single reflection, means the error is like not fully considered or not fully corrected. Okay, so this is my first question. So my second question is like, so if you look into errors, as I just mentioned, it's still can reach around like 10 meters, right? So what do you think is the potential solutions to further improve the accuracy?
To further improve the accuracy, if I go to here, there is, I think there is supposed to be a methodology. So for the, I think for when you look at the particle filtering, I think when they're doing the particle filtering, they should be able to eliminate more of the particles which are not related or not close to the reference position. And also, I think that's for the, I think also for, they should be able to find a way. I think we should be able to find a way to more likely use more of the multiple reflections. So notice what are the multiple reflections and find the errors in that.
Yes, yes. Let's say one point. For example, to identify the multiple reflections, and also that you can combine more sensors like with camera, maybe with LiDAR, with IMU to improve the robustness and also together with the accuracy.
Yeah.
Yes.
So
okay. Yeah, that's great. That's all my questions.
Okay.
Okay. Thank you again.
No worries.
So let's move to the next one. Yeah, the next one is Tan Chung Chen. Yes. You're ready. You're starting to ready.
Good morning, everyone. I'm Tam Jun Shong, and I will introduce a 3D version at GNSS LTK positioning for autonomous system in urban canyon. First, let me to introduce the background. The accurate and global reference positioning is one of the crucial components of autonomous navigation system, including the autonomous driving and ground vehicles. And LOAD using onboard local sensors such as camera, IMUS or lighting detection, and LiDAR to enhance the accuracy and robustness in challenge environments. And however, the high cost of the 3D LiDAR sensor is one of the major problems, preventing its full deployment in automatic system. And moreover, the LOAM positioning is subject to inevitable drift in long-term operation. Therefore, the study team proposed a method which is integrate the GNSS RTK positioning and VINS to address the problem. And the VINS is combines the visual data from camera with IMSS US measurement for accelerometer and gyroscope to estimate the position and orientation of moving object. And the RNSS RTK positioning introduce a significant higher degrees of absolute positioning accuracy with the assistance of current phase measurement and correction for the reference station. However, it is some problem of the GNSS RTK to use in autonomous system in driving. And the first problem is the number of available satellites may be limited in urban canyon due to a signal blockage caused by surrounding building. In this situation, the geometry of the satellite's distribution is destructive, which would cause a large ADOP. And the second problem is the most of the GNSS signal received in highly upper area are NLOS reception that typically emerge under condition in which direct light of slide signal transmission is blocked and reflect signal from the same satellites are received. Therefore, the accuracy of the flow solution estimation based on double different current phase and shadowing measurement is degraded. And to address the problem, the study team will improve the lower with using the lower lying visual landmass measurement to give a better geometry contrast for GNSS RTK, and then they will do the system integration to combine the VINS and the GNSS. And here is the photo of their integration. They will combine the pre-integration of the IMUS and the measure modeling, the vector graph autonomous VI initialization. And the method consists of two parts. The first part is the GNSS NLOS outline removal. And the second part is improving the geometry with visual landmass measurement. And the first part, they will use the UNet for their sky view image with a white and black panels denoting the sky and non-sky area. The satellites can be projected on the segment image based on their elevation angle and the heading from north of Earth of the sky polling camera. Then we will use the healthy LOS measurement and ignore the NLOS signal. For the improving the geometry with visual landmark measurement, the estimator general by integrate the measurement for IMU pre-integration, lower lying visual landmass reprojection from the forward-looking camera, and healthy GNSS LOS measurement from a vector graph-based sliding window optimism. And there's the 5 types of the vector involved in generate the vector graph, and the red and green circle denote the DD shooter range and carrier phrase vector, and the purple and light blue rectangle denotes the IMU pre-integration and Doppler vector, and the blue 6-point star denote the visual landmark. The IMU pre-integration technology was employed to integrate several measurements into a single vector between 2 consecutive frame BK and BK plus 1. The resistance is expressed as this. And we will use the visual landmark vector, and the visual measurement employed in this study is a set of features identified by shine to Mosaic corner algorithm. After the feature detection, the optical flow feature tracking algorithm was performed to track them between contrasticity. And here's the reprojection receiver module can be derived at this equation. And is the DD shooting vector. And you can see the result this equation, and the RSRT is to represent the GNSS receiver and the satellites S and W. And the PWL RT, B is the position of the IMU body frame related to the world local frame at RT. And here is the DD carrier beta brace vector. And here is the GNSS Doppler vector, and is the equation of the residual. And the ESRT is represent the LOS vector connecting the GNSS receiver and the satellite S. And after the free vector, we can do the optimization, and we'll use the WLS estimation to find the residential. And here is some different part of, such as the IMU pre-integration, the visual reprojection, and some DD shadowing vector. And after the optimization, and we will do the we'll combine the linear module, connect the flow solution, and separation can be expressed as this equation. And the B and C is represent the set of IMU and visual measurement. After then we will do the VI initialization. The initialization of system state is significant for an estimator with higher nonlinearity. Because we only need to do the once time to when the systems start up. So the VI initialization, including the recover of the scale of the feature, as well as the bias of the gyroscope, accelerometer, and other elements. And the outcome of the VI initialization, including accept position and velocity of the keyframe inside the sliding window, denoted by two equation. And we will also do the GNSS VI initialization, because the GNSS VI initialization aims to generate an initial guess for various GNSS related stage, including integrate, integer, ambiguity, receiver clock bias, draft rate, and the extremity parameter between the ENU frame and the well local frame. But however, the carrier phrase is not adapt for this GNSS VI initialization, because therefore we need to develop a new carrier phrase measurement for satellite S, and here is the equation. And the K is represent the size of the sliding window. It means the satellites, the RN GNSS receiver continue for K epochs. And the MS outcome T is defined for P. And here is the receiver of the ambiguity 3DD current phase measurement. And after the finish the setup of the new DD carrier phrase, and we can the trajectory and velocity set of the sliding window can be estimated based on Doppler and DD pseudo range and ambiguity free carrier phrase measurement in this equation. And to verify the effectiveness of the proposed method, the experiment will conduct in Arbor Canyon in Hong Kong. The experiment contests static building, trees, and dynamic object to generate GNSS and LOS reception. In this experiment, the student team will use the GNSS receiver, INU, and also prepare a forward-looking monocular camera to capture the visual feature, and a sky pointing fish eyes camera to capture the sky view image. And we will use 5 methods to collect the data. And the first is the RTK, which is a conversion method. And the RTK NE is the conversion method, which is to remove the NOLS signal. And the RTK NEVINS is doing the remove the NLOS signal and integrate the VINS. And the RTK IG is the RTK IG is improve the geometry contrast by visual measurement with the GNSS measurement. And the RTK NEIG is also remove the GNSS NLOS reception and improve the contrast by the visual measurement with healthy GNSS measurement. And here is the data and the performance of the position performance. And as you can see, there's some mean error of 1.83 meters were obtained using conventional GNSS RTK positioning method with a standing deviation of 2.01 meters, and the maximum error reached 13 meters by a dash rectangle. And the RTK-NE methods, the error decreased to 1.78 meters, representing only a 2.7% improvement compared with conventional RTK methods. And the average DOP value for the satellite distribution is about 3.1 and 3.5 before and after the GNSS NLOS exclusion. And as you can see, the RTK-IG and the RTK-NEIG is much better than other three methods because their main error was less than other method. And here is the rotation performance of four methods, including three methods, including RTK-NE-VINS, RTK-IG, and RTK-NEIG. And the main error of 5.80 degree was obtained using RTK-NE-VINS with a standing deviation of 3.57 degrees. With the RTK-IG, the mean error of attitude decreased to 3.01 degrees with a decreased standard deviation of 1.71 degrees. And moreover, the main attitude error decreased slightly to 2.73 degree using GNSS NLOS exclusion by RTK-NEIG. And here is the AD-OP measurement to indicate the result measurement. And as you can see, the table is compared to the successful rates of the integer ambiguity resolution to four method. The RTK-IG and RTK-NEIG were much better than other two methods. And the RTK and RTK-NE only had 12.64 degrees and 10.59 degrees. And because the initialization of extra parameter between the ENU and local world frame is significant for the performance of the state estimation due to the high nonlinearity of the system. To verify the effective of the proposed initialization method in double and high accuracy DD current phase measurement are applied. Therefore, the study team compared the two methods. One is the weight last square based and double current moving. And error is, as you can see, the error of the 15.70 degrees of the yaw offset was obtained using the conventional method, and the Using the proposal method, the area of the Yao offset degree to the 5.93 degrees. Therefore, all the area errors decrease by using double carries moving method. And in conclusion, the integration of VINS and GNSS RTK is a potential solution that may provide accurate, cost-effective, and drill-free position for autonomous system with specific navigation requirement. And there are several directions for future work on the subject. For example, how to fix the GNSS RTK positioning in previous April and develop a model of multi-path effective.
Okay, so this paper is hard. And this paper is super hard. I can see your efforts to try to understand all those equations. So how many time do you spend to prepare a slide? I mean, prepare a slide includes the reading the papers and try to understand the papers. 1 week, so right? Okay, yeah, quite honest. Yeah, I mean, one week is still very hard to understand all these things because this paper has a lot of equations. So generally, I think, man, because you have sent your slide to me, I have provided some general comments, quick comments to you. I mean, by today. So can you go back from the first page? Yeah. Okay. So yeah, you can. Of course, you can add your names and student IDs in the first page. So your name is Tan Chen Cheng, yeah. So next page. Okay, yeah, this is good. You provided the background or the outlines. Okay, next page. Yes. Okay, next page. Yeah, okay, I think I love this page. You try to just illustrate the main problem this paper focus on. Okay, the first one is the geometry problem. The second one is the satellite measurement quality problem. Okay, next page. Okay, next page. So yeah, I think this is a good video. So when you do your presentation, just quickly skip this one, right? You can mention a little bit to the audience that, okay, so this is a video, so you can refer to this video with details about the presentations for this paper. Okay, this can be good as well. Okay, next page. Yes, but still, I would say this paper is hard. It's hard to read. So yeah, you have a lot of equations. Yeah, next page. Yeah. Yes, that's the first part. Yeah, yeah, okay, for your slide. So it can be great if you can like add more maybe figures maybe some figures to improve the readability of the slide. For example, for this page, you can add some figures about the Doppler factor. For example, you can add the figures about the Doppler measurements, about the Doppler effect. Okay, something like this. Okay, next page. Yeah, this one is about the state of the system. It means the unknown variables you want to estimate. This page is also hard to understand, but in this page you are too quick. You just quickly skip this one. But in fact, you need to clearly explain each variables if possible, because this is one of the most important pages for your presentation. Because the state means the unknown variable you want to estimate. Okay, next page. Yeah, that's good. This is a model. Yeah, next page. Okay, next. Yeah. Okay, so yeah, this page is also very important, but the visual landmark factor is very hard to explain because it includes the reprojection factor, reprojection process. Okay, next page. Yes, this is a double difference should range. Okay, next page. Yeah, let's see the carry face. Okay, next page. Yes, I know this equation is quite how to explain the physical meanings of the equations. So yeah, I would say it's okay. Yeah, next page. Yeah, this equation is very important. So it's good that you like add a subtitle for each equation. For example, the marginalization factor, IMU pre-integration factor, visual projection. So it's good to explain this one in detail. You can next page. Yes, next page. Okay, next page. Next page is good. Yeah, but still, it's the equations. It's hard to like explain everything in detail in 15 minutes. Okay, next page. Okay, so yeah, roughly. Okay, next page. Let's finish all the slide first. Okay, about the experiment. Okay, it's good. So in this page, it can be good if you can explain the figures a little bit more. For example, you can say, so the first experiment is in urban Kenya 1. So this one is like the mid-urban Kenyas. So next one is like dense urban Kenyas. You can introduce a little bit more if possible. Yeah, next page. Okay, yeah, it's good if you add the full names of all those solutions. Yeah, next page. Yes, to see the results. Okay, next page. Next. Yes, I good. Next page. Yeah, this one is also very difficult to explain because, for example, for heat maps, it means something, but it's hard to explain. Yeah, next page. So for this one is the differences between this is about the initialization. So this is also hard to, but at least you would say you can say like okay, from second current to the third current, the accuracy is improved. Say something like this. Okay, next page. Okay, so that's the conclusion, right? The fixed genes are decompositioning in the previous epoch. Okay, yes. Let's see last page, right? Okay, so my last question. So when you prepare the slide, okay, so what do you think is the most important thing you have done by doing this?
I think, in my opinion, is the I think it's the GNSFBI initialization. Yeah, it's so I think it's the most difficult part to understand and why we need to revise the 3D current phase measurement because therefore I'm so doubt for this actually.
Yeah, at least you try, right? Because this paper, you see, so this is a paper coming from a PhD student. So it's it's like a work. For example, PhD have finished the undergraduate, finished the master degree, and finally he start his PhD and spend the first 2 years to build the foundations. And in the last year, the PhD student finished this paper. So of course, it's hard to fully understand. So go back to my question. So I mean, this is very difficult, but you try to understand this part, right?
Yes.
Yeah, it's you're great. You're great. But still, I mean, yes, yeah. If I really want to make one more comment, is like again, this paper is hard. Okay, so 1 week may not be good enough. Maybe like if you have more time, you can have like in the future if you have a similar project, you can spend like 2 weeks to prepare a slide. So in this case, you can have a better understanding for this paper. And also if you have time, you can arrange one more meeting. For example, if you prepare a slide for 2 weeks, in the first week, you prepare a slide and go to your professor and to have a meeting with him or her to see if any comments from professors and improve it again. So if I have to make a comment, I will say this. Okay, thank you again for your presentation. Okay, take break for 10 minutes.
Or like visual solution. It's more concentrated system, more constellations, including like GPS, BDS, runners, and familiar. Yeah, this is one point. Still, I mean, for example, if you combine the multiple satellite system, maybe you can increase the error meters to about 8 meters. This means the accuracy is still about several meters. So to further improve, you need to combine more efficient sensors. Yes. Also, this is remote. It's already 8 years before. Yes. Okay. So can you copy a slide? The slide be ready. Okay, so you can start if you're ready.
Okay. Testing. Okay.
Good afternoon, everyone. Today I'll be presenting LEO-SAM, a tightly coupled linear inertial odometry system developed by Tixiao Shan and several others. LEO-SAM represents a state-of-the-art approach to real-time trajectory estimation and map building, which plays a crucial role in robotics and autonomous systems. Let's now dive into the details of their work. LEO-SAM is designed for real-time trajectory estimation and map building, as I have just mentioned. The system tightly couples linear and inertial data within a vector graph framework, allowing it to incorporate loop closures and GPS measurements seamlessly. This improves mapping accuracy while maintaining real-time performance. One of its standout features is its use of a sliding window approach for efficient keyframe management, which significantly enhances its computational performance. Localization and mapping are fundamental for mobile robots to perform tasks like feedback control, obstacle avoidance, and path planning. While vision-based SLAM methods rely on cameras, they are sensitive to lighting conditions and initialization. In contrast, linear-based methods like LOM excel in capturing 3D details but face challenges such as drift and inefficiency in feature-rich environments. This research addresses these limitations by building on LiDAR and inertial data fusion techniques. The authors of LEO-SAM contribute significantly to the field of robotics and autonomous navigation. First, they propose a tightly coupled framework that integrates linear and inertial odometry using a vector graph. Now, this approach allows for efficient multi-sensor fusion, enabling the incorporation of various measures, including GPS, loop closures, and even compass data. Second, they introduced an innovative sliding window method that processes a fixed number of keyframes, ensuring real-time performance while maintaining accuracy. This approach minimizes memory usage and computational overhead. Third, LEO-SAM electively approach minimizes memory usage and computational overhead, and also focusing computational resources on recent data. The final contribution is contribution is extensive experimental validation, where LEO-SAM is tested across diverse environments and platforms, including handheld devices, ground robots, and also boats. These contributions make LEO-SAM a highly robust and scalable solution for mobile robotics. Now, this figure shows that the system architecture and show the system's architecture and showcasing the interplay of key components like EMU pre-integration, LiDAR odometry, and also GPS vectors within the vector graph. LiDAR inertial odometry systems have evolved significantly over the years. They can generally be categorized as loosely coupled or tightly coupled systems. Loosely coupled systems such as LOM and LEGO LOM possess LiDAR and EMU data separately and only integrate the results in a basic optimization step. While these methods achieve real-time performance, they are prone to high drift and also lower accuracy due to the lack of joint optimization. In contrast, in improved accuracy, in tightly coupled systems like LIOM, Johnny optimized LiDAR and emu measurements, resulting in improved accuracy. However, LIOM also struggles with computational efficiency, running at less than real-time speeds. LaoSam builds on the strengths of tightly coupled systems while addressing their computational limitations by combining efficient keyframe selection, sliding window optimization, and loop closure detection. LaoSam achieves both real-time performance and high accuracy, making it a practical solution for field deployment in diverse environments. LaoSam organizes state estimation as a factor graph of optimization problem. The state of the robot at any time includes its rotation matrix R and position vector P and velocity V, and also emu bias B, as shown in this equation. Sensors such as a 3D line, an emu, and optionally GPS provide measurements. These inputs are integrated into the factor graph, which represents the problem as a series of nodes and constraints. Emu pre-integration factors capture motion between frames, while LiDAR odometry factors ensure spatial alignment of point clouds. Now, GPS and loop closure factors correct long-term drift, especially in environments with limited features. Optimization is performed using ISAM2, a real-time incremental smoothing and mapping algorithm. This efficient system structure allows LaoSam to handle data from multiple sensors while maintaining real-time performance. Its ability to incorporate absolute measurements such as GPS and compass data makes it adaptable to various applications, from urban mapping to search and rescue. Emu pre-integration is a key component of LaoSam, enabling accurate motion estimation even in dynamic environments. As LiDAR scans are affected by motion during capture, skewing them is crucial for accurate mapping. The equations shown here describe the angular velocity and acceleration as measured by the emu. These raw measurements are corrected for bias and noise. Pre-integration provides relative motion estimates which serve two purposes. First one is skewing point clouds and providing an initial guess for LiDAR odometry optimization. By integrating these constraints into the factor graph, LaoSam achieves joint optimization of LiDAR and inertial data. This process ensures that the system maintains robust to motion artifacts, improving the overall accuracy of mapping and trajectory estimation. Emu pre-integration also enables the system to operate effectively in GPS-denied environments where relative motion estimates are essential for maintaining localization accuracy. LiDAR odometry in LaoSam involves extracting edge and planar features from point clouds. These features are matched against a sliding window of recent sub-keyframes rather than a global map to improve computational efficiency. The distance between features and their corresponding edges or planes is minimized using the equation shown here. These transformations are used to align new LiDAR frames with the existing map. And this process ensures high local accuracy while maintaining real-time performance. By selecting only keyframes where significant motion occurs, LSAM reduces memory usage and also computational load. This approach is particularly effective in feature-rich environments where global map matching will be computationally prohibitive. Now, linear odometry is a critical step in the vector graph as it provides the spatial constraints needed to accurately position each new frame. The combination of linear odometry and emu pre-integration allows LSAM to achieve both precision and also efficiency. To validate LSAM's performance, experiments were conducted across diverse platforms: a handheld device, a ground vehicle, and a boat. These platforms allow the system to be tested in urban, natural, and water environments, each presenting unique challenges. For instance, the handheld device allowed for rapid translational and rotational movements, while the ground vehicle tested the system's robustness on uneven terrain. The boat, on the other hand, experiments focus on handling sparse features and GPS intermittency in the canals of Amsterdam. Now, table 1 here summarizes key details of the datasets used in the experiments, including trajectory lengths, elevation changes, and also maximum rotational speeds. Now, the figures here highlights the three sensor platforms employed. These varied setups ensure that the LSAM was evaluated under realistic and demanding conditions, demonstrating its ability to adapt to different environments while maintaining accuracy and also efficiency. The rotation dataset was designed to evaluate LSAM's robustness during high-speed rotational motion. The test involved holding the sensor suite stationary while performing aggressive rotations at speed up to 133.7 degrees per second. Now, these figures compares the mapping results of LOM and LSAM. LOM struggled to preserve structural details in the map, as its loosely coupled system couldn't handle rapid rotational effectively. In contrast, LSAM maintained fine structural details thanks to its tightly coupled framework that integrates emu pre-integration and LiDAR odometry factors. This dataset highlights LSAM's capability to accurately register each LiDAR frame in rotation matrix, even under challenging rotational conditions. Such performance is crucial for applications where robots experience rapid changes in orientation, such as aero drones and handheld devices. The walking dataset tested LSAM's ability to handle aggressive translational and rotational motion in SE3. The sensor suite was carried across the MIT campus at a maximum translational speed of 1.8 meters per second and rotational speed of 213.9 degrees per second. Now this figure compares mapping results from LOM, LIOM, and also LEOSAM. LOM diverged multiple times due to inaccuracies in point cloud registration. LIOM, while better, produced blurry maps and failed to run in real time, achieving only 0.566 real-time performance. LEOSAM, however, produced maps consistent with Google Earth, and it effectively incorporated loop closure, and GPS factors to eliminate drift. This dataset underscores LSAM's ability to handle fast motion while delivering real-time accurate mapping. a significant advantage over other systems. The Canvas dataset demonstrated LSAM's effectiveness in environments with intermittent GPS availability and significant drift potential. The user carried the sensor suite around the MIT campus, capturing a trajectory filled with buildings and trees that obstruct GPS signals. Now this figure shows that the trajectory comparison and map alignment. LOM suffered from substantial drift, while Leo GPS corrected some drift using GPS but failed to close the loop when GPS was unavailable. LSAM excelled by integrating loop closure factors into its factor graph, correcting drift even without GPS. The map produced by LSAM aligned closely with Google Earth imagery, as shown in here, 5B, figure 5B. And Table 2 compares the end-to-end translation errors, where LSAM achieved the lowest error of just 0.12 meter, demonstrating its superior drift correction capabilities. The PARC dataset tested LSAM's performance in a feature-rich environment with varied road surfaces and intermittent GPS signals. Sensors were mounted on a ground vehicle driven along a forest trail with asphalt, grass, and dirt-covered roads. Now, this figure here highlights the trajectory comparison and map alignment. LOAM and LIOM suffer significant drift as no reliable absolute corrections were available. Now, LSAM, on the other hand, utilize loop closure factors to correct drift, producing an accurate map aligned with Google Earth. In addition to handling complex terrain, LSAM achieved real-time performance with minimal computational overhead. Now, Table 2 here also shows that LSAM's end-to-end translational error was only 0.04 meter, highlighting its ability to operate effectively in dense GPS challenge environments. This dataset underscores its applicability for outdoor navigations and mapping. In Amsterdam dataset, sensors were mounted on a boat navigating the city's canals. Challenges included sparse features, intermittent GPS, and sunlight interference. Now, figure 7 here shows that LSAM's successful map alignment with Google Earth, sorry. LOAM and LIOM fell entirely in this scenario, emphasizing the system's capability to handle extreme mapping conditions, environments. Table 3 here compares the RMSE translation error relative to GPS, with LSAM achieving the lowest error. Table 4 highlights the runtime performance, where LSAM consistently processed LiDAR frames in real time and handle up to 13 times real-time data playback. These results demonstrate that LSAM balance accuracy and efficiency, making it suitable for real-world deployment. In summary, LSAM is a highly accurate and efficient system for LiDAR inertial odometry and mapping. It performs well in diverse environments, outperforming existing methods like LOAM and LIOM. Future work could involve testing the system on unmanned aerial vehicles to further extend its applications. Thank you.
Okay, it's you make use of 20 minutes already. Okay, so I just have one quick comments like, so your slide is great, very clear logic, but the main problem is you can add more interaction with the audience. Yeah, just looking into your scripts, you need to have more interaction with the audience. So these are my main comments. So generally, your slide is well designed with very clear logic. Okay, thank you again. So let's move to the last presentation from Hao Yang. Okay.
Okay. Today I will talk about the urban positioning for 3D mapping added GNSS using dual frequency shooter range measurement from smartphone. And here is a content background, methodology, experiment, and conclusion and future work. First is the background. There are some challenges in positioning in urban chaos. For example, the multipass and the non-line of light unloss effect, and also the low-cost GPS receiver equipped on the smartphone also introduced the problem of receiving some unhealthy measurement. And however, here are some new positioning approaches. For example, first is the 3D mapping added 3D MA GNSS by applying 3D model, 3D building geometry to predict the satellite visibility and the path. It includes the shadow matching and ranging based 3D MA GNSS, and the ranging based further includes the likelihood based and the sky mask, and also the ray tracing, but we will not cover this. The second is the GNSS L5 band signal, which has a higher chipping rate and shorter chipping lines compared to the commonly used L1 signal, and it can mitigate the multipass effect. So the solution proposed is to address the non-loss effect by the 3D MA GNSS, but the 3D MA cannot address the multipass effect. So we will use the L5 band signal to address it, and then apply this to the 3D MA. The 3D MA has the shadow range and the range-based 3D MA. The shadow range is shadow matching is better in cross road direction, and the range-based 3D MA is better in a long road direction. So we will integrate them together to have a final solution. And here is the models. First, an overview of the L1, L5 3D MA GNSS model. First, we will replace the shooter range and carry to noise ratio of the L1 with the L5. And second, the position candidate selection should select within this circle of the radius of 40 meter and the separation of 2 meter based on the per-generated candidates considering the sky mask. And the third is the the calculation of the score of the candidate. It goes through this process, and we got the score. And the high score is means that we trust more on this candidate, and we add more weight to it. So we can calculate by this weighted average for with the candidates and its score to calculate the position solution. So how we get the score is very important. Here is a flow chart, but we can see from the candidate's distribution to the candidate scoring, there are two paths. One is the shadow matching, and one is the range-based 3D MA. We will first talk about the range-based 3D MA. It is to simulate the total range of all satellites for each candidate, and the high score will be given to the candidate with the closest simulated total range and the measured total range. First, let me define the total range difference as the measured total range minus the model total range. And so here is the score, and it's the exponential of this one. This one is the weighted geometric mean square error, and inside it, this is the total range difference, and this Q is the diagonal matrix, including the uncertainty for every satellite, and the uncertainty is calculated based on the carrier to noise ratio and the elevation angle. A higher elevation angle means that the satellites are less likely to suffer from the multipass effect. And there are a tuning for L5 band signal, since the multipass effect of L5 is 10 times smaller than the L1 brand. So we add a factor of 10 here to trim the uncertainty. A second path is the shadow matching, which compares the visibility of the receiver satellite and the visibility predicted on each candidate to get the score. First, we should calculate the ability the possibility of being a lost satellite. It is based on the building boundary and the carrier to load ratio. And then we can calculate the score based on this equation for the candidate G. And so how we get the modeled shooter range in order to calculate the shooter range difference. This equation we are very familiar with, but here is a constant. It's for tuning the L5 signal because the L5 signal has a different wavelength with the L1 signal. But however, there are two very important unknowns I want to emphasize. One is the receiver clock bias. It is here. There is two approaches to deal with it in this paper. And another one is the delay for non-loss reception. And here is also two types of ranging-based 3D MA to focus on it. I will first talk about the modeling of the receiver clock bias. And first approach to estimate the receiver clock bias is using single difference, and is already talked in the lecture. But I want to emphasize that the choosing of the reference satellite is very important, since if an error exists in the selected reference satellite, the error will then be cumulated in all other satellites. And how we select it, we can select based on the carrier to noise ratio, and the elevation angle, and any surrounding buildings, or just based on the position candidates. However, the second approach is the weighted lattice square with the inter-constellation offset estimation. I will mainly focus on the IC offset estimation. We can see here is the receiver clock delay vector. The first term is GPI's receiver clock delay, and the other term is the inter-constellation clock delay between GPIs and other constellations. And it can also be calculated as this one, and where the A is the design matrix consists of the flag. The flag is to indicate whether a satellite belongs to this constellation. However, if the inter-constellation error can be estimated by using the data from the reference station, and the satellites will be considered as one constellation. As a result, for the same receiver, the receiver clock error will be the same for all the satellites, and we only need to use one satellite for calculate the SD. And also, the A matrix reduced to a column vector of C, and we can substitute into this equation to calculate the SG. And SG is simply the receiver clock delay. And we get this. And second, I will talk about the modeling of the NLOS error by the ranging-based 3D-MA. The first is the SkyMask 3D-MA GNSS. So what is SkyMask? Here's an example. This is the building boundary, and here is two angles that we can get from. And for this method, we first feed the non-loss satellites azimuth and average angle to this enhanced SkyMask, which consists of the building height information and the AARP. It can calculate the position of the reflect point, and if we got the point, we can calculate the error by the total distance of the reflect point minus the distance between the satellite and the candidates, and then we can substitute into the modeled shooting range, and then the shooting range difference, and finally got the score of this type. And the second method is the likelihood-based ranging. We should first select a satellite for the reference to calculate the SD, and then use the candidate's SkyMask to estimate the visibility. For the NLOS satellites, the equation is given here. And for this type of satellites, the NLOS error is much larger than other error. So we can regard these two terms are the same. So this equals to the minus of the error. And we can remap this shooting difference to the likelihood shooting difference, and then we can get a score of this type. So how we integrate? For integrating two range-based 3D MA, we can use this logic. If the reflect is found by the SkyMask, we can use the SkyMask shooting range, but no found, we will use the likelihood shooting range. And for the integration of the SDM and the range-based 3D-MA, we will integrate the score, and then we can calculate this position by the weighted average. We talk about it. And then is the experiment results. First comparison is between the L1 and L5 banded signal. And here is the residual difference. We can see from this graph that the L5 banded signal have much better performance for the low elevation angle. For example, the J8 and the J3, you can see this line, lower line. And J3 is suffer from the multipass effect, so we did an experiment for the J3. We can see from here for the L5 band signal, there are this average shooting range difference and this fluctuation. And so this is more accurate and more stable, and it proves that L5 is less affected by the multipass. And also applying the L5 can benefit to the 3D-MA to improve the concentration of the likelihood candidates. And second comparison is made between the different approach to get the receiver clock barriers. And here are 5 approaches, the IC indicate whether it's used the IC offset, and the P indicate whether it is use the loss subset only. And here we can see the no use of IC, and this figure is large, so the IC offset has a better estimation, and also the method 1 and method 4 have better performance. So we take a closer look at them. We can see that the mean and the standard deviation and the maximum is much smaller for the WLS than the SD. It's maybe because of the SD you only use one satellite to do the difference. However, the WLS apply all the satellites. For the heat map, you can see, although for the SD, the high score candidates are more concentrated, the area is small, which originally means that the is more accurate. However, actually the high score particle drift away from the ground truth, so the WLS is more accurate, and we will apply this method. And last is the integrated position result. We can see that the integration of these three approaches can get relatively accurate results. The orange is around the green star. And also for the integration for the sky mask and the likelihood, although the likelihood-based ranging has least concentration of the high score candidates, the integration can only keep the common high score candidates, so the result is good, and it's further integrated with the SMD, is improved. However, there is a problem. The integrate may not always be may not always result a good positioning. It can add uncertainty actually. You can see from the range-based 3D MA to integrate with the SDM, the high score candidates area actually increase and the concentration reduced. For the conclusion and the future work, the conclusion is the IO5 ground signal can mitigate the multipath effect. And second, the PWRS IC method is relatively better for estimation for the receiver clock barriers. And this paper proposes the 3D MA GNSS integration method on shadow matching and ranging-based 3D MA, including the sky mask and likelihood-based ranging. For the future work, the team want to determine the parameter of the 3D MA based on the quantitatively factors, and they want to try to introduce filter graph optimization into the 3D MA GNSS, and also they want to exclude the unreliable candidates. And finally, they think the integrated results can be utilized as the initial position and visibility estimation in the RTK. And thank you.
Okay, so Heyang, thank you for your nice presentation. I think yeah, I can fully recognize you spent a lot of time to read this paper to get familiar with the slide, because you fully look into the slide and make your presentations. So again, I think you can have more interaction with your peers and with your audience in doing the presentation. So this is my first quick comments. So I think you have very clear logic for introducing this paper, because this is a very good paper to introduce the 3D MA, the SDM with the AirFi signals, and also you provide very detailed comparisons in terms of the the residuals or errors of the AF5 signals compared with the AL1 signals for the different satellite systems. So I think also the time is roughly you spend like 70 minutes. I think it's generally it's good time control. So because it's almost 20 minutes, I just have one more quick questions. So can you go back to the conclusions? So okay, so in here he mentioned like okay, so he mentioned several like conclusions, several one of the okay, next week. Sorry, next slide. I mean the future work. So in here he mentioned several aspects like for example the compiler factor graph optimization to improve the accuracy instead of the iterative distributing the candidates. So from your point of views, so do you have any ideas to improve the accuracies of this paper? Just say anything appear in your mind. For example, in this paper, they only use the GPS, right? So do you have any ideas like how to improve the accuracy further?
Maybe we can use relative navigation system such as IMU, LiDAR.
Yes, that's a good point. So because if you look into the results, the error can mean the potential error of this paper can still reach around like 10 meters. I mean, at least this is not sufficient for the self-driving cars, right? So still has a lot of rooms to improve. For example, you can combine the sensor from relative positioning or from the LiDAR or camera stuffs. Okay, thank you again for your presentations. So I think this is roughly all for the presentations. I think by this week we have finished all the presentations. Yeah, I will take this. So yeah, this is the last week for this course. So yeah, if you have any questions for the final exam, feel free to send email to me to make an appointment with me. Okay. So yeah, if there's no questions, see you in the final exam. Okay. Good luck with you. Okay. Good luck. Yeah, feel free to dismiss. Okay. Feel free to dismiss.